Chapter 6 Eigenvalues. Let's start section 6.1 Eigenvalues and Eigenvectors. Suppose we have a square matrix A. Consider the system AX equal to lambda x. Here, lambda is a scalar. X is a non-zero vector. If we have the scalar lambda and the non-zero x satisfy this equation, then we call lambda is an eigenvalue or characteristic value of A. And the vector x here is called eigenvector or characteristic vector associated with the eigenvalue lambda. Here are 5 equivalent statements for a square matrix A and a scalar lambda. The first statement says lambda is the eigenvalue of the matrix A. The second statement is the system A minus lambda Ix equals 0 has a non-trivial solution. Here, I is n by n identity matrix. The third statement is the Lie space of A minus lambda I is not the same as the zero subspace. Statement 4. A minus lambda I is non-singular. Number 5. Determinant of A minus lambda I equals 0. These 5 statements are equivalent. They are used to characterize the eigenvalue lambda, and also we can say the eigenvector x in the second statement. Let's prove the 5 statement equivalent. First of all, let's look at the first statement. Lambda is the eigenvalue of A. Is equivalent to the system A minus lambda Ix equals 0 has a non-trivial solution. Here's the proof. Lambda is the eigenvalue of A means Ax equals lambda x for a non-zero vector x. And we can say if we move lambda x from the right side to the left side, then we get this system is the same as the second statement, A minus lambda Ix equals 0. Here again, x is a non-zero vector, and this just means the system has a non-trivial solution. Because if we look at the second system here, we can easily say if we pick up x equals 0, for sure that's the solution. That solution is called the trivial solution. But for this system, if it has a non-zero solution, then that solution is called a non-trivial solution. Let's say the second and the third statement are equivalent. Statement 2 is the system A minus lambda Ix equals 0 has a non-trivial solution. That means there is a non-zero vector x 0. such that a minus lambda I x0 equals 0. Here x should be x0. That's equivalent to say x0 belongs to the Lie space of this matrix A minus lambda. And that's the same as the Lie space of the matrix A minus lambda I not equal to 0 space or 0 subspace. The equivalence between the second and the fourth statements. The second statement says the system A minus lambda x equals 0 has a non-trivial solution. And the fourth statement says the matrix A minus lambda I is singular. Now this equivalence, we can prove it just by applying theorem 1.5.2. The equivalence between statement 4 and statement 5. Statement 4 says A minus lambda I is singular. Statement 5 says the determinant of the matrix A minus lambda I equals 0. These two statements are equivalent. We can apply theorem 2.2.2 to verify this. So in this way, we proved the 5 statements for a scalar lambda are equivalent. Let's consider an eigenvalue of the matrix A. Then the Lie space of the matrix A minus lambda I is a subspace of Rn. Now this subspace is called the eigenspace corresponding to the eigenvalue lambda. That means what? That means here we can have not just the one single eigenvector for the eigenvalue lambda. We actually corresponding to the eigenvalue lambda, there is a subspace. That subspace is a Lie space of the matrix A minus lambda. Now, we will see this later examples. Characteristic polynomial. Here we define a polynomial P lambda as the determinant of the matrix A minus lambda I. Recall, I is an n by n identity matrix. So from this, we can say this characteristic polynomial is actually a polynomial of degree n, because A is n by n, I is n by n, so that the matrix A minus lambda I is n by n matrix. Now, this matrix contains n lambdas on the main diagonal. From that, we can say this determinant is a polynomial with respect to lambda, is a polynomial of degrees n. Characteristic equation. We define the equation by the determinant of the matrix a minus lambda I equals 0. So essentially, this equation associated with the polynomial. We wanted to find the lambda. Lambda is the root of the polynomial or characteristic polynomial P naught. So this equation, we can get n eigenvalues. Those are the eigenvalues of the matrix A. Example 1. Prove that n by n matrix is singular if and only if lambda equals 0 is the eigenvalue of the matrix A. The proof here is simple, just by the definition. A is singular, we know that's equivalent to its determinant is 0. Here, after A, we add a term minus 0 times identity matrix. 0 times any matrix, we get 0. So that this is same as the determinant of A0. But here, if we think about 0 means a scalar lambda equals 0, then we can say this is equivalent to say lambda is the solution of characteristic polynomial P. And that means lambda is an eigenvalue of the matrix A. We recall we proved 5 equivalent conditions for a scalar number to be an eigenvalue of matrix A. Example 2. Let's consider matrix A. Now this matrix A we can say is a 3 by 3 matrix. We want to find its eigenvalues and corresponding eigenvectors. First step, we need to find the characteristic polynomial. That means we need to evaluate the determinant of the matrix A minus lambda I. Here, I is a 3 by 3 matrix because A is 3 by 3, so I should have the same size as the matrix A. So here is the matrix A minus lambda I. Lambda just appears on the main diagonal, so that we get on the main diagonal we got 2 is the A11, so 2 minus lambda times 1. And here this is A22 minus lambda times 1. And this one is A33 minus lambda times 1. And then the rest of the diagonal entries we could say. For this determinant, we can find its form. This is equal to lambda, negative lambda times the square of lambda plus 1. Then we need to find the eigenvalues of matrix A. Now to do this, we need a third characteristic equation. Now from this we can say the y at the last step we write down the characteristic polynomial as this kind of form, or we factor like this, is because after we factor the characteristic polynomial as this form, then we can easily find the solution, or we can easily from here find the eigenvalues of matrix A. So from this we can say determinant of A minus lambda equals 0. For that we can get lambda equals 0 and lambda equals 1. Now lambda minus 1 square equals 0. So for that we can get two solutions are identical. So in this way we write down the first eigenvalue is 0. The second and the third eigenvalues are the same, that equals 1. Then we need to find corresponding eigenvectors for the matrix A. So let's start with eigenvalue lambda 1. Lambda 1 equals 0. So to find eigenvectors associated with lambda 1 equals 0, we need to solve the equation A minus lambda 1 I x equals 0. But lambda is 0, so that we need to solve the equation ax equals 0. To do this, we write this kind of form: A minus lambda 1 I then dash 0. The left side is the matrix A minus lambda 1 I. Then the right side is actually this 0 in the system. Because lambda is 0, or lambda 1 is 0, so that this is just matrix A. And the right column here is 0 vector in the system AX equals 0. What we're going to do is we're going to use elementary rule operation to work on the left side of this matrix. Now to do this, we can take a look at the first row. We use the first row minus the third row. So in that way we get 2 minus 1, we get 1. And then negative 3 minus negative 3, we get 0. And then 1 minus 2, we get negative 1. And the last value here not change because that's just 0. So in this way we get the first row here. And then we can use the first row here minus, or the second row minus the first row, and in that way we can get the values will be, this one will be 0, this is negative 2, and then the third value here is 2. So the value here is 2. And then do the same thing from the third row minus the first row, and you can say we will get this is a negative 3, and then this is a 3 here. Then divide by the third, then divide the third row by the negative 3, we got negative 1, 1. Then the second row we use to change the first row minus the second row, then we get this is -2 and 2. Then divided by the -2 for the second row, we get this. And then take away in the third row by -3, we can get the last row is 0. Anyway, just by elementary row operation, you can get this form. The most important thing is the last row is 0. The last row is 0. So that here, after the row elementary operation, we got the system here will be x1 minus x3 equals 0. And the second one will be x2 minus x3 equals 0. So we need to solve these two equations. To do this, we can take x1 equals alpha. Then from the first equation, x1 equal to x3, we get x3 equal to alpha. And then x2 equal to x3, that's alpha. So that we got the solution for this system x equals 0 is equal to the vector with entries 1, 1, 1 times alpha. Alpha is arbitrary scalar. So from this, we can say associated with the eigenvalue lambda equals to 0, we have infinitely many eigenvectors. Those vectors have this kind of form. Now, when we talk about eigenvector, we say eigenvector is non-zero. So except for alpha is 0, all of this are the eigenvectors associated with eigenvalue lambda is 1. Because of this, we talk about eigenspace. So the eigenspace associated with lambda 1 is the subspace spanning by the vector 1, 1, 1. So that's the 1, 1, 1 vector. Step 4. Let's find the eigenvectors associated with the eigenvalue lambda 2 and lambda 3. Recall, lambda 2 and lambda 3 are equivalent, both equal 1. Now, to do this, we need to solve the system a minus lambda 2I times x equals 0, or a minus I times x equals 0. We use the same just as we did in step 3. So here we make a 3 by 4 matrix. On the left side, that's the matrix A minus lambda 2I, or A minus I. Then the right side is the 0 vector on the right side of the system. And then this one we can easily use row elementary operation because from this we can say the 3 rows actually are the same, so that we can just simply from the second row take away the first row. We got the second row here 0. Do the same thing. The third row, we take away the first row. We got the third row 0. So in such a way, after the row elementary operation, we got the system now is just the 1, negative 1, 1 times x1, x2, x3 equals 0. So we just need to solve the equation x1 minus 3x2 plus x3 equals 0. Here just the equation, not equations. Now, in this case, we can say we have just one equation, 3 variables. That means we can arbitrarily choose 2 values among x1, x2, x3. So here, let's say we choose x1 equals alpha. Alpha is arbitrary number. And x2 equals beta. Beta is arbitrary scalar. Then from this we can get x3 will be equal to negative x1 plus 3x2 equals negative alpha plus 3 beta. So that the solution for the system A minus I times x equals 0 is of this form. Alpha is the first entry, then beta, the third entry is 3 beta minus alpha. Now for this, we can rewrite this vector as a linear combination of the scalars alpha and beta. So here you can say we pick up alpha, so that's got a 1 here and 0 here and negative 1, so that's the first term. And then we got the second one where we think about alpha is 0, then we got 0, 1, 3 times beta. In this way, we can say, again, corresponding to eigenvalue lambda 2 and lambda 3, we have infinitely many eigenvectors. Those eigenvectors of this form. Now for that, the alpha, beta not the same time equals 0, because we require a eigenvector is a non-zero vector. So we have infinitely many choice. Each of those is an eigenvector associated with the eigenvalue lambda 3 and lambda 2. From this, we can get the eigenspace corresponding to eigenvalues lambda and lambda 3 is the subspace spanning by 2 vectors. Now, these 2 vectors, you can say that's from here. That's from here. Because we use the linear combination of these 2 vectors. So that's why we say that's the subspace or the eigenspace is spanning by these 2 vectors. That's how we write down the solution, or how to write down the eigenvectors and eigenspace. Here, this should be stated as 0. We consider the product and the sum of the eigenvalues. We assume lambda 1, lambda 2 to lambda n are the eigenvalues of m by n matrix A. Why we got n eigenvalues? Because the characteristic polynomial is a polynomial of degree n. Degree n, we should get n roots. by the Gauss theorem, so that we have n eigenvalues for the matrix A. Then we can get the product of these n eigenvalues is the same as the determinant of matrix A. Recall A is a square matrix, so we can have its determinant. And then the second equation tells us the sum of these n eigenvalues equal to the trace of the matrix A. The trace of matrix A is the summation of the n diagonal entries of the matrix A. So TRA, that's for the trace of A is defined as the sum of A11 plus A22 plus to the ANA. So that's the trace of the matrix A. Here's the proof. First of all, the characteristic polynomial P lambda has degree n because A minus lambda I is n by n matrix. The lambda appears on each row, each column just once, so that we can say this polynomial has degree n. So that it has n rows for the polynomial. We call that lambda 1, lambda 2 to lambda n. These are the eigenvalues of the matrix A. And then we can fact the polynomial as the product of lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda n. Why we can do this? Because we know all the solutions, so that the polynomial can be fact as a product of this form. The only thing we need to find is the scalar alpha in the front. That's the coefficient we needed to find. Once we find the lambda alpha in the beginning, then we get the factorization for the characteristic polynomial P lambda. Actually, we can say alpha is the leading coefficient of P lambda. What means the lead coefficient? Because what? Because this polynomial here has degree n, so that the first term will be the term related to the lambda to the power n. So that is the lead coefficient. In this way, we can say the alpha should be equal to negative 1 to the power n. Why negative 1 to the power n? The reason is we need to look at the determinant here. So here you can say we have the polynomial defined as the determinant of A minus lambda I. Now, if we look at this product, we can say on the main diagonal, that's A11 minus lambda. That's the first entry of the main diagonal entry. And then the second will be A22 minus lambda, followed by A33 minus lambda. And the last one is AN minus lambda. Now, those n terms make product, we can get the power for the negative lambda to the power n. So in that way, we can say alpha here equals negative 1 to the power. That's the lead coefficient of P naught. And then from this, we make a switch because alpha is negative 1 to the n. So we change lambda minus lambda 1 by lambda 1 minus lambda. So we get this form. And then we have a negative 1 times this one, we change by this term, and the last one, negative 1 times this, we get this. So in this way, we can say the characteristic polynomial P lambda actually equals the product of lambda 1 minus lambda and lambda 2 minus lambda to the lambda n minus lambda. From this, we can consider a particular value for lambda. If in this form we take lambda equals 0, then we can say that will be lambda 1 minus 0, so that's just lambda 1. And then the second term is lambda 2. The last term is lambda n. So P0 equals the product of lambda 1, lambda 2 to lambda n. But P0, recall, P lambda equal to the determinant of A minus lambda I. When lambda equals 0, then that's the determinant of A minus 0. So that P0 actually equal to the determinant of A. So in this way, we got the first equation, which says the product of lambda 1, lambda 2 to lambda n equals the determinant of matrix A. Then we consider the second identity. In this case, we look at the characteristic polynomial P lambda. By definition, the characteristic polynomial equals the determinant of matrix A minus lambda I. So that's the form for the determinant. Now, for this n by n matrix, what we're going to do is we're going to expand this determinant calculation by the first column. So that will be equal to A11 minus lambda. So this entry times the determinant of M11. M11 is the minor of this entry. So that's actually this one. That's this entry here. And then we should plus A21 then times negative 1 negative to the power 2 plus 1, then times the determinant of M21. M21 is the minor of A21. And then continue this way, we can go to the n1 times the negative 1 to the power n plus 1, then times the determinant of the minor of an1. So we get this form. From this, we can say here AI1 doesn't have lambda involved. Just look at the determinant of MI1. We can say this determinant here is a polynomial of lambda 1. And let's take a look at the minor of A11. So let's just look at this. Let's look at this matrix here. Now, for this matrix here, we can say it has lambda on the main angle here, So from this we can say this minor, the determinant of M11 should be a polynomial of degree n. Then let's look at the minor of A21 or M21. Now in this way, the way to get its minor is cross the second row, because A21 on the second row, and then cross the first column. Then from this we can say we get rid of on the second row the lambda got off, and then the first column got lambda off. So look at the rest of the parts. We can say we just have n minus 2 terms involved the lambda. So from this we can say the determinant of M21 is a polynomial of degree n minus 2. That's n minus 2. Now, from this we can say the first term here, A11 minus lambda, for the lambda the power 1, and then the determinant of M11 it is a polynomial of degree n minus 1. So put this together, we get this is to the power lambda n. Then the rest term here is just the polynomial of degree n minus 2. From this, we can say A11 minus lambda times A22 minus lambda times AN minus lambda is the early term in the expansion of the characteristic polynomial involving product of more than n minus 2 of the diagonal elements. Because what? Because here is just the n minus 2 degrees for the polynomial. So only the first term here get the polynomial, the power is n minus 2, higher than n minus 2. Because what? Because the first one, so A11 minus lambda, then times this determinant of M11 degree is minus 2. And then for this one, we can expand. So for the M11, if we expand according to the first column, then we should get A22 minus lambda times this part take the determinant, and continue this way. So that's what we can say. Here, just this form is the early term in the expansion, has the power more than n minus 2. Now let's look at the power for lambda to the n minus 1. In this case, we can say the coefficient for the negative lambda to the power n minus 1 is A11 plus A22 plus to the AN1. Just expand this product. We need to look at the power for the lambda 1 to the power n. So in that way, that means what? That means we look at, for example, lambda 1, so pick up the negative lambda from the first term, then we can get the terms for the rest term here. For example, the first term we pick up negative lambda, then the second term we pick up negative lambda, then to the last term here, we should not pick up negative lambda because we need the power to the n minus 1. So pick up negative 1 from the first n minus 1 terms, and then the last term we pick up the non-lambda term, so that's a n n. So in that way we get a n n. And then we do the same thing, for example, for n minus 1 terms, we pick up negative lambda, but the n minus 1 term there, we pick up a n11, n11. So that's we get the second term here. And the same thing, for example, the first term here, we pick up a11, then the rest terms we pick up negative lambda, negative lambda, lambda. So that's get to the negative lambda to the power minus 1. So that term is a11. So a11, a plus a22 plus ann, that will be the coefficient for negative lambda to the power minus 1. And also we can look at this from a alternative way to look at the coefficient of negative lambda to the power n minus 1. From where? From the polynomial p lambda. Recall on the last page, we showed the p lambda is the product of lambda 1 minus lambda 2 minus lambda to the lambda n minus lambda. So from that, we can say the coefficient of negative 1 to the power negative lambda to the power n minus 1 is lambda 1 plus lambda 2 to the lambda n. So in this way, these are two representations for the coefficient of lambda, negative lambda to the power n minus 1. They should be same. They should be same. That means the sum of eigenvalues equals the trace of matrix A. Example 3. This example 3 you can find from exercise 6.01, question number 4, or at the end of the chapter test B, question number 3. We consider a n by n, n means the n here, an n by n non-singular matrix A. If lambda is the eigenvalue of A, then the lambda is not equal to 0. Second, 1 over lambda is the eigenvalue of the inverse of matrix A. If x is the eigenvector of A associated with the eigenvalue lambda, then x is also an eigenvector of the inverse of A associated with this eigenvalue 1 over lambda. Here's the proof. First, because lambda is the eigenvalue of A, so that lambda is a solution for the characteristic polynomial p lambda. In this case, we can say the p lambda equals the determinant of A minus lambda r. So from this, we can say if lambda equals 0, then p lambda equals 0. P 0 equals 0 means the determinant equals 0. In that case, A is singular. So that from this we can say because the assumption A is non-singular, so that we cannot get lambda equals 0 is the solution of the characteristic polynomial. This is the one proof for the first property. And actually, we can use the property we just showed earlier. Recall, the product of all eigenvalues equals the determinant of the matrix A. Determinant of A is not zero because A is non-singular, so that the product is not zero. Product is not zero, then all factors, all the eigenvalues are not equal to zero. So that's the second way to show an eigenvalue of the matrix A is non-zero. Because it's non-zero, then we can talk about its inverse. Here we want to show 1 over lambda will be an eigenvalue for the matrix A inverse. Let's say X is the eigenvector of the matrix A associated with the eigenvalue lambda. Then by the definition, we should have this equation. Ax equals lambda x. X is non-zero. And then both sides here, we multiplied by 1 over lambda times the inverse of A. Because lambda is non-zero, so 1 over lambda makes sense. A is non-singular, we can find the inverse. And in this way, we can get this product. Do the multiplication from, this should be from the left side. From left side, then we can say A inverse times A, that's equal to I. And in such a way, we can say the left side will be 1 over x. Then the right side equals 1 over lambda, then lambda and lambda here cancelled, we get A inverse times x. So we got this form. The inverse of A times x equals 1 over lambda times x. Recall, x is non-zero. From this equation here, we can say, by the definition, we can say here 1 over lambda is an eigenvalue for this matrix A inverse. And the x is an eigenvector associated with this eigenvalue 1 over lambda. So we proved both the second and the third statement. Let's look at theorem 6.1.1. This theorem is about similar matrices. We talk about the similar matrices in chapter 5. We consider two n by n matrices A and B. Suppose these two matrices are similar. Then the conclusion is these two matrices have the same characteristic polynomial, and they have the same eigenvalues. Here's the proof. Since A and B are similar, by definition, we should have a non-singular matrix X. A non-singular matrix X, such that A equals the inverse of S times B times S. Then from this, we want to show the characteristic polynomials of A and B are the same. So here is the polynomial, the characteristic polynomial of A. By definition, that equals the determinant of the matrix A minus lambda I. I is n by n matrix, identity matrix. And then we substitute here A by S inverse times B times S. And the identity matrix I by S inverse times S. And then here we can say both these terms share with the factor S inverse and also S. So we can rewrite this difference as S inverse times the bracket of B minus lambda I, then times S. And then we got three matrices product take a determinant that we know equals to take a determinant separately. So the first matrix take a determinant, second matrix take determinant, the third matrix take determinant, and then mixed product. But the determinant of S inverse equal to the determinant of S to the power negative 1. So that's times the determinant of S, we get 1. So that in this way, we get the determinant of B minus lambda I. This, by the definition, that is the characteristic polynomial of the matrix B. So from this, we can say the two characteristic polynomials are the same. The two polynomials are the same. Of course, their roots are the same. Their roots are the characteristic values or eigenvalues for these two matrices. So in this way, we proved the theorem. Then the question is how the eigenvectors of these two similar matrices A and B are related. For this, let's look at exercise 6.1, question 26. The question says like this. We assume A is an n by n matrix and B equals the inverse of S times A times S. Now from this we can say because we have S, a matrix, it has inverse. That means B and A are similar. The reason why here we not just say A and B are similar, but precisely write down B equals S inverse times A times S is because we want to have this following conclusion. If X is an eigenvector of the matrix B associated with the eigenvalue lambda, then S times X is the eigenvector of matrix A associated with the eigenvalue lambda. First of all, let's say why we write it down like this. Recall in the theorem 6.1.1 we proved when A and B are similar, then they have the same eigenvalue. So that here we can say the lambda is the eigenvalue of matrix B, and also we can say the eigenvalue associated with matrix A. The conclusion is this. If X is the eigenvector of B associated with lambda eigenvalue, then S times X is an eigenvector associated with the eigenvalue lambda. Now from this you can see why we specify B equals S inverse times A times S, because we need this matrix S here times X. because x is a eigenvector, x is non-zero. S is a non-singular matrix. Non-singular matrix times a non-zero matrix, S times x is non-zero. So that we can say that's the format in this question. To prove this, we start the assumption. In the assumption, we say x is the eigenvector of B associated with the eigenvalue lambda, so that we can write this statement by the equation B times x equals lambda times x. And then what we're going to do next is we're going to replace B by this form. So we got S inverse times A times S, that's B times x equal to lambda x. And then both sides we multiplied S from the left. Then we can say S times S inverse A times Sx equal to S times lambda x. Now here, this is a very important statement. Multiplying by S from the left. Why from left? Because what? Because here x is n by 1 vector. N by 1 vector we cannot multiply by S. We just can multiply the S from left because this left side is n by n. So we can multiply that by n by n matrix. So this statement from the left is important. And then we can say S times its inverse equal to identity matrix, so that we get A times Sx equal to S times the lambda x. Lambda is scalar, so we move from. So in this way, we get this form. A times Sx equal to lambda times Sx. Now here we use blue ink to emphasize Sx. Sx is a non-zero vector, so that by the definition we can say here lambda is a eigenvalue of A, and Sx, you can say here left we have Sx, right side we have Sx. Sx is a eigenvector associated with the eigenvalue lambda. So in this way, from the definition of eigenvectors, we proved Sx is an eigenvector of the matrix A. Example 5. We assume A is an n by matrix, and the matrix B equals A plus I. I here is n by n identity matrix. The question is this, in this case, is it possible for A and B to be similar? The answer for this is no. To explain the reason, we consider in a positive way. Suppose A and B were similar, then from the theorem 6.1.1, they should have the same characteristic polynomial. So the determinant of A minus lambda I, that's the characteristic polynomial for the matrix A, should be equal to the determinant of the matrix B minus lambda I. This is the characteristic polynomial for the matrix B. but by the assumption b equal to a plus I, so that we do the substitution here, and then we have 1 times I here minus lambda times I here. So we put this together, we get a minus lambda minus 1 times I. Now in this way we can say if we assume lambda is a eigenvalue of the matrix A, then from this side we can say lambda minus 1 is also a eigenvalue of the matrix A. Now continue this way, we can say this. If lambda 0 were an eigenvalue of A, so that means the first part equals 0, then the second term should also be 0. That means lambda 1 minus 1 is also an eigenvalue of A. Then here, the first part, we substitute lambda by lambda 0 minus 1. Then this right side, we should get lambda 1 minus 1, that's lambda 0 minus 2, should also be a solution. And then continue this way, we let this lambda equal to lambda 0 minus 2, then here we get lambda 0 minus 3. So in this way, we will get infinitely many eigenvalues. That from lambda 0 is the eigenvalue of A, we can get lambda 0 minus 1 is the eigenvalue of A, and lambda 0 minus 2, lambda 0 minus 3, lambda 0 minus n, continue this way, that's impossible. So in this way, by contradiction, we answer this question. In such a kind of case, A and B could not be similar to each other. That's all.